So the example problem says a flue gas containing 200 kg of air and 0.0325 kg of aluminium oxide at 50 degrees centigrade and 1 atmosphere pressure has to be scrubbed using 400 kg of water at the same temperature and pressure. So it is at 50 degrees centigrade and 1 atmosphere pressure. The aluminium oxide powder has logarithmic PSD mesh between 0.1 to 10 micron with 100 intervals. The powder is having standard deviation of 1.5 micron and mean of 5.8 micron. So this is the problem statement, and we have to perform these 3 tasks, or these 4 tasks rather. What are they? First, we have to design a Venturi scrubber with rectangular throat of width-height ratio of 2 to achieve exactly 95% separation efficiency. And we have to use Calvert calculation method. Then we will take a 100 millimeter long throat and simulate using Young calculation method. So the first one is a design problem and the second one is the simulation problem. In the third problem, we have to change the model to spray tower. So first 2 things we will do the Venturi scrubber, and the third problem will shift to spray tower with 2 millimeter orifice diameter at 90 degree angle, and we have to find the shorter mean droplet diameter and relative gas velocity. And they are asking how many nozzles would you need to obtain 0.05 millimeter shorter diameter. So this is also a kind of design problem. In the first problem, what should be the shorter mean droplet diameter? In the second, we are specifying that we need 0.05 millimeter shorter diameter, and in order to have that, how many nozzles we need. So this is the problem in short. So we will go to Aspen and let us enter those data. Okay, so let us go back to the main flow sheet. So we have to enter the data. First, go to the properties. Al2O3. It will have air and water. These 3 things are there. Right. Obviously, this will be solid. Another 2 are conventional. We'll go and choose the methods, which is solid, and run. Okay. Now let us go to the simulation window once again. Go to the setup, fix up your PSD. Now what is PSD? We have logarithmic PSD mesh between 0.1 to 10 micron with 100 intervals. So we have logarithmic 100 intervals for 0.1 to 10 micron. So here we can use mu or you can use micron, whatever you want is the same. Create PSD. Right. And we have to choose the stream class also. So choose mix CLPSD. So these 2 are defined. Now go to the stream and set the feed. Feed is at 50 degrees centigrade and 1 atmosphere pressure. So it is 50 degrees centigrade and 1 atmosphere pressure. It has 200 kg of air. So air is 200 kg, and solid, this will also have 50 degree. This will have 1 atmosphere pressure. Mass flow rate will be 0.0325. So it is 0.0325. And the particle size distribution we have a normal distribution with standard deviation 1.5, mean 5.8. So 1.5 and 5.8 both in micron. Okay, calculate. Done. So the PSD curve is done. Now go to the liquid inlet. What is the liquid inlet? It is 400 kg of water. So here also it is 50 degrees centigrade, 1 atmosphere pressure, and 400 kg per hour. Okay, so feed condition is set. Now go to the block of scrubber. Now, first thing first, we have to use the Venturi scrubber in design mode. So we will use Venturi scrubber in design mode, and rectangular throat will be used. Width to height ratio of 2. Width to height ratio of 2 for rectangular, and separation efficiency we need 95%. Okay, so by giving this, all our information is set. So it is very straightforward, not much information needs to be given, and we can run it. Okay, so results are available. Let us go to the stream results. Yes, so we'll check the mass flow rate. Let me check. In the feed, you have 0.0325, and in liquid out, how much of aluminum oxide is there? 0.030875. So you have to find the ratio of this by, not this one, this. Okay, so if this is A, this is B, so A by B, what is this ratio? This ratio is 0.030875 by, this is the inlet, 0.325, and it is expected to be 0.95. Let us perform a simple calculation. Yes, it is 0.95. Okay, so that is the separation efficiency we are looking for. So it has done the calculation and it has given. Now air, almost all the air, it is going through the clean gas. Only some portion of air is going through the liquid out. Okay. And unfortunately, some amount of water is also going through the clean gas. Okay, so it is not able to collect the entire mist. If you want to see the particle size distribution of Cl gas, then you can just see what is left. So this is the particle size distribution. If you check the particle size distribution, you can see over here. So the green line is the feed and this one is liquid. The red line is liquid. So feed and liquid, they almost overlap each other. That suggests that 95% of the particulate matter has shifted from the gas phase to the liquid phase. It has been arrested in the liquid phase. The clean gas is also having some amount of particulate matter and its distribution is something like this. Okay. Now let us go to the second problem. Second problem says, take a 100 mm long throat and simulate using Young calculation method. So we shift to Young method and that also you have to give it to the simulation method. Okay. Right now we have to provide the throat length of 100 mm long. So it is 100 mm long. And we are having a short of some information. We have to provide certain values over here. In the previous method, we were using the rectangular throat with width and height ratio of 2. So we have to provide the information of width and height size. So let us provide that information. Let us take throat width to be, say, 20 mm and height to be 10 mm. So that makes the width versus height ratio to be 2. Okay. So let us run this system and we find results available with warning. So what is the issue? Let us go back and check over here. It says the gas velocity is more than maximum. So much gas velocity cannot be given. Okay. So we have to reduce the gas velocity. So let us increase the throat size and check. So let us go to input and make it 40 by 20. Let us run it once again. Yeah, now it is available. So you understand the problem. When your throat size is smaller, the gas velocity is very high. So it was a problem. So the maximum gas velocity that Aspen can allow over here is 120. So we have increased the throat width and height. Now the simulation is possible. Okay. So you can see the results. Your separation efficiency has gone to 98.9. Earlier we have defined it for 95%. Now we have given us condition where we are able to achieve 98.9% of separation efficiency. Okay. And remember the gas velocity entering the throat is now 63. Earlier it was 240 something. Now it has reduced to 63. Now let us see the third problem. It says, change the model to spray tower with 2 mm orifice diameter at 90-degree angle. Find the sorter mean droplet diameter and relative gas velocity. Right? So change to spray tower. So let us choose the spray tower and then the orifice diameter of the nozzle is 2 mm and it is 90-degree angle. So it is 2 mm and 90-degree angle. And we have to find the sorter diameter. So we have to check, calculate the sorter diameter. Okay. And here you have to specify the relative gas velocity as well. So we do not have any information about that. Let us use this one, 63.6. Let us give some other value. Let us give the value of 60. Okay. Now here you notice, even after giving all the necessary information, it still says that required input incomplete. So what is the reason? Reason is, you remember I told you that Young type calculation method is not applicable for spray tower. So we cannot use this Young type calculation method. Instead, we have to use Calvert type calculation method. Okay. The moment we choose Calvert, then this input is complete. Now we can run the system. Okay. So run it and we find some error. Let us check what is the error. So the error is wash fluid pressure needs to be larger than the gas inlet pressure. Now again, what is the wash fluid pressure? This is 1 atmosphere. The liquid pressure is, the water pressure is 1 atmosphere. And what is the feed pressure? Feed pressure is also 1 atmosphere. Air is going in with 1 atmosphere pressure. If both of them are 1 atmosphere, then how the nozzle can spray liquid? Water pressure has to be very high, then only we can spray, right? That is exactly what it says. So we have to increase the pressure of liquid. So we, instead of 1 atmosphere, let us use say 2 atmosphere. So water is sprayed at a higher pressure. And run the system once again. And now the results are available. Okay, so let us see the summary. Here again, you see the solder diameter. It is 0.18 millimeter. And what is the nozzle diameter? We had chosen the nozzle diameter to be 2 millimeter. 2 millimeter orifice diameter, okay, of the nozzle. So for 2 millimeter orifice diameter, we are getting 0.18 millimeter solder mean droplet diameter. And separation efficiency is almost 100%, is 99%. Okay. But how many nozzles are there? Only one. We are using only one. So entire simulation is being done with only one nozzle. So the fourth problem, they are saying that how many nozzles would you need to obtain 0.05 millimeter solder diameter? So here they are asking you to design. Okay. So go to the input once again. Put it in design mode. And specify the solder diameter to be 0.05 millimeter. So actually, if you see the result, it was showing 99.634. We can give the same value. And we want the number of nozzles to be calculated. Okay. So we give the separation efficiency as before, but we have reduced the solder mean droplet diameter from 0.18 to 0.05 millimeter. Okay, so this is our desired. So we have to design the scrubber so that the solder diameter of droplet has to be 0.05 millimeter. Run the simulation with that. and see the results. As expected, the solder diameter has become 0.05, but how many nozzles we need? 25 nozzles. Okay, so they are saying that we have to have 25 nozzles to arrive at this solder mean droplet diameter. And our separation efficiency is kept as before. And relative gas velocity has gone up to 203.438 meter per second. It has gone to very high condition. Okay. So this is how you work with scrubber. So you can design your scrubber as well as simulate the scrubber if you have enough information. Okay. And this way you can practice further. So with that, we come to the end of this lecture. I hope you have enjoyed it. And we'll come back with yet another interesting lecture very soon. Thank you.